Welcome to this episode of the Structural Engineering Channel podcast, a podcast focused on helping structural engineering professionals stay up to date on technical trends in the field and to help them succeed in their careers and lives.
In this episode, we're talking to Professor Karen Scrivener, a research group leader at the Swiss Federal Institute of Technology, Lausanne, or EPFL, and expert on cement chemistry and material science of cement-based materials. She'll be talking about alternative ways to reduce the carbon footprint of concrete to tackle concrete's CO2 problem, and we'll also talk about her career and research that she has been doing. I'm your host, Matt Picardo. I'm a licensed engineer at DCI Engineers practicing on structural projects in California with an undergraduate degree from Cal Poly Pomona and a master's in structural engineering from UC San Diego.
And I'm your co-host, Alexis Clark. I work in Hilti's North American headquarters as the product manager of our chemical anchoring portfolio in the US and Canada. I'm a licensed professional engineer in Texas. I received my bachelor's in civil engineering from UT Austin, and I'm currently an MBA candidate at Auburn. And now I would like to introduce our guest for this episode, Professor Karen Scrivener. Professor Karen Scrivener came up with the idea for LC3 cement in 2008. This material has the potential to cut CO2 emissions related to cement by more than 400 million tons a year. She obtained her PhD at Imperial College in 1984. She's worked for Lafarge in France for 6 years before being appointed professor and head of the Laboratory of Construction Materials at EPFL in Switzerland in 2001. Her research focuses on understanding the chemistry and microstructure of cement-based materials and improving their sustainability. In 2003, she founded the research network Nanosem, bringing together the leading industrial companies, cement and admixtures companies, with European academic institutes to do research on cementitious materials. She was made a fellow of the UK Royal Academy of Engineering in 2014. Now, let's jump to our energetic conversation with Karen.
Karen, welcome to the show. We briefly introduced you to our guests earlier on in the show, but in your own words, can you tell us a little bit about what you do on a daily basis and what your research entails?
Yeah, I mean, right now I'm spending most of the day stuck behind this computer screen, but I think that's the same for most people around the world. Normally I work at EPFL, which is a university in Lausanne in Switzerland. It's a very international university. And I have a group of about 25, 30 people who work with me. So these are mainly PhD students who are following, various projects, various research projects. So it's a very diverse job. I mean, working with the PhD students, advising them in their work. Recently, there's been more and more travel. Of course, that's all disappeared the last couple of years. But, particularly since we've been starting working on this new cement type, we've tried to get out into the field because, it's no good having a good idea if you just keep it in the lab. You've really got to get people to apply it in practice. And that's led me to a lot of countries I've never been to before, which has been very interesting. But, I always find it incredible to meet the people there and discuss concrete. Sounds really nerdy, but that's kind of what we do.
It's a good thing. I think you're in the right place. I think we might have a couple of eager beavers here that want to learn more about concrete and the work that you do there. So bringing that to actually our next question, I understand that you put together a network called Nanosem that brings together leading companies that work on nano and micro analysis and understanding of materials. Can you tell us about this network and how you arrived to generating it?
Yeah, well, it's quite an interesting story. I mean, I started work as an academic. I was a professor at Imperial College in London. And then this was about 1995. I kind of, was a bit fed up. I didn't see where it was going. Clearly working on concrete, it's something that's used in the real world. And I wasn't convinced where the applications of our research was. And I had the opportunity to go and work for Lafarge, which is a very big cement company. So I moved over to France, to Lyon in France, and worked in their research lab for 6 years. And that was a really challenging and dynamic experience, but I really learned a lot. And then in 2001, I had the opportunity to come back to academia here where I am now in EPFL in Switzerland. And, you know, when I did that, I also kind of said to myself, well, look, I really want to keep this link between academia and industry, because, you know, we've got here a material which is the most used material in the world. It's a very, very important material. And there's no point doing research if at some stage it can't have some application. So, you know, I also saw that the cement industry as a whole had kind of abandoned more kind of long-term fundamental work for, you know, a couple of decades. And so this sort of fact that there had been a lack of fundamental research, and then the increasing awareness of sustainability and CO2 and climate change meant the, you know, the environment was right. I spent a long time going to visit the major cement companies who are mostly European and convincing them to join this network. And then really, I think the network got going. 2004 was when we were really up and running. And, you know, I think this has just brought about a really a radical change in the kind of research that is supported by the industry. Rather than short-term research projects, they're now thinking much more strategically. What is the kind of fundamental science they need to do to understand the mechanisms behind that? I mean, that's why we call it Nanosem. That's a little bit outdated now, perhaps, but nonetheless. Nanosem's kind of actually now in the process of winding down, but I mean, that's not because people have decided not to support it. I'm very pleased that, in fact, now it's been kind of had a bit of a takeover. It's been taken over by the Global Cement and Concrete Alliance, GCCA, who have formed a research network in Innovandi. And, you know, pretty much all the partners of Nanosem have moved across to Innovandi. And now we've brought in a lot of other partners outside Europe. So we've got many more cement companies involved, many more academics, including like China and India. And I mean, this is just fantastic, because I think this is now, you know, now the challenge to get to lower CO2 is more and more important, and being able to, you know, bring people on board and do much more serious long-term projects in this network is just fantastic.
I love that. And I think it's so impressive. It's so amazing that over time, your group Nanosem has kind of found other external partners to grow with and to combine efforts and really make a larger effort towards green cementitious materials. So I think that's fantastic. I do have a really quick deviation that I'm curious to ask. Most of the time when we speak to academics or people who are within the realm of academia, they tend to be very focused, and most of their career has been within research and educational institutions. You have this deviation where you went to industry. I'm curious, to those structural engineers who we have listening who are in academia, how do you think that time in industry has shaped your steering of research after having had that experience?
Well, totally. I mean, you know, as I said, when I left academia, I was kind of disillusioned, because we would meet people from the industry, and they would kind of say, "Oh, this stuff you're doing in academia, I mean, this is just not relevant." And so I'd say to them, "Well, you know, what should we be doing?" And they never gave me an answer. And, you know, I thought they didn't give me an answer because it was all super confidential. Well, when I crossed to the other side of the fence, then I realized it's much more because they didn't actually know. I mean, they had things they were dealing with in everyday life, but they didn't really know how to translate that into the underlying scientific questions. So, you know, that's kind of where I saw this great opportunity, because seeing how things were in the field and then linking that to my, you know, my background in material science, and, you know, being able to put the whole lot together, you know, I just gave me this great opportunity, which is what I've been kind of working on for the past 20 years or so.
Fascinating. Thank you so much for that. I appreciate that perspective because I feel like most of us within this structural engineering or materials science realm, we're one or the other. Like we're all about industry or we're all about academia. And I think that there's a lot of value to having a perspective from both sides of that fence, right? And making us a better professional having had that experience and that perspective.
I think there's a real benefit. I think the problem is it's becoming tougher and tougher to do it. The pressure on academics to, deliver in terms of publications really means that it's really difficult to go to industry and then get the chance to come back. I think I was very lucky, and probably now with the next generation, it's becoming very tough. I mean, I was also lucky because I already had a kind of somewhat established reputation as an academic before I went to industry. And, I was there 6 years, but, I still was going to conferences and keeping up my network and everything. So that made it comparatively easy to come back. And I think that opportunity is not really so available to people. It's really a shame. But again, I think, through this network of Nanosem and now Innovandi, this also helps a lot because it really gives the opportunity for a much more extended dialogue between academics and industry on a kind of continuing basis. And I see that as being very fruitful.
Yeah, I definitely agree. I can definitely relate with in the industry where it's, well, what do you guys need? I feel like in the industry, we have our tools already and we don't know where those tools came from. So we just use those tools to design. So when you ask that question, it's like, well, I don't know, these are the tools I have. I wish I had better tools, but like we just want to design and I can definitely relate to that. Like if you ask us that question, well, we're not really sure. That's why I think that dialogue and that network that you built is definitely important because even just having that network with the academia and the industry, it's the dialogue. It's essential because it's kind of we're feeding off of each other and helping each other out. So I did want to transition to your idea for LC3. Could you tell us more about that and why you think it has so much potential?
Well, I mean, again, this whole question of sustainability, CO2, climate change has just been creeping up and up the agenda. I remember when I moved to EPFL, it was just when Al Gore was, promoting his film, An Uncomfortable Truth or something like that, which really kind of brought it to the attention. And then with Nanosem and with the industry, we really started analyzing, well, what were the possibilities? And this is what's, really interesting to me because, we see in the press all these articles about, this wonder solution. And when you really sit down and analyze what the possibilities are, you realize there is not any wonder solution. We're talking about a material, there's more concrete produced than all other materials put together. Something like 40 billion tons a year. And 90% of that is used in emerging or developing countries, not in places like the US or Europe. US and Europe probably account for like 10% of world CO of concrete consumption. So if you're really going to impact this, there's no point coming up with some kind of fancy solution that can be used, by a very few people in one of these, where even in USA and Europe, I mean, if you go down to a building site, things are not that sophisticated either. So, we have to come up with practical solutions that really work. And then we started looking, well, what are the possibilities? And then you realize that we're ultimately constrained by the composition of the planet. And it's incredible. I mean, I must have said this statement over 1,000 times, but the Earth's crust, 98%, is composed of just 8 elements. That's oxygen, silicon, aluminium, iron, calcium, sodium, potassium, magnesium. Just 8 elements is 98%. And clearly, you're not going to make a material which is used in such huge quantities by looking in this remaining 2%, because we haven't got enough of it. It's going to be way too expensive, everything like that. And so, you go from the composition of the earth, you then have to consider, well, how does cement works? And, it's actually quite an interesting concept that you have something that reacts with just plain water at room temperature. And first of all, it dissolves, like when you put sugar in your tea, it dissolves. But then you get these new compounds forming called hydrates, which precipitate. So you have something that dissolves and then precipitates. Now, okay, you've got these 8 elements, and you say, well, which of these elements really give you this property to dissolve, react with water, form these hydrates? And you come down to really a system of 3 oxides, of calcium oxide, of aluminium oxide, and silicon dioxide. So, this is amazing, because you've gone from the whole earth and you say, well, you can really only make cements out of these 3 oxides. It sounds way too simple, but honestly, this is the reality. And then you realize that you can't really produce anything better than the Portland cement we produce today. Perhaps we'll talk about some of the other possibilities later. But, this Portland cement we produce today is just incredibly efficient at giving you this reaction that solidifies everything. So, okay, we've got that far. We see Portland cement's very good. We need to stick with it. And then you say, okay, what we can do and what's very effective to reduce CO2 is to replace as much as we can of that Portland cement with something else. And again, this is not new. We've been doing this for quite some time. We're using things like, I'm sure your listeners know about, like fly ash, which comes from burning coal, and slag, which comes from producing iron. The problem is that, if we take slag and fly ash, the amount of those we have available today is quite small compared to the production of cement. So we are using those compounds, and that's great, but we can't go much further with that. And then we say, well, where can we find other substitute materials? And the answer to that is really the only thing that's out there is clay. And with clay, when we calcine it, that's to say we heat it up to a temperature of about 800 degrees, it becomes a very reactive material. And again, that's not new. This has been known probably for 100 years. But what was the real breakthrough with LC3, we realized partly from some fundamental work we've done in Nanosem, that the aluminium component of the clay would react with limestone. So if we put calcined clay and limestone together, we could actually go to much higher levels of substitution than just the calcined clay on its own. So in fact, you can take out 50% of the Portland cement in, ordinary cement, and you can replace by this combination of calcined clay and limestone, and you can actually get stronger materials, on the time scale we're talking about, 28 days. And in fact, it overtakes it usually in a week or so. And then other properties like resistance to chloride penetration, ability to deal with alkali silica reaction, which is a major problem. These are also vastly improved. So, this was really kind of something very exciting. We had developed this, in a funding program from the Swiss National Science Foundation, but supported by the Swiss government part that deals with helping developing countries. And they said, well, this is exciting. You should try and make it work in the field. So then we went mainly to India. We partnered up with some people in India. This is the advantage of having a network. I had one of my former PhD students who's now professor in Indian Institute of Technology in Delhi. And him and some other institutions, they really took this up, and they did all the field work in India. And, that's not easy. So that's really how we got the whole thing together. And now we're working with in about 50 different countries around the world. And last year we had the first 2 commercial productions starting, one in Colombia in South America and one in Ivory Coast in Africa. But I think that's really just the start of what we see as an exponential growth. We see several companies are going to do pilot productions even in Europe this year. There's at least 3 projects to start producing these materials in North America. So I think we're going to see in the next 5 to 10 years, this is really going to become a big part of the cement market.
Wow, I'm just like in shock right now. I love the way you described that. The way that you kind of holistically talked about solving this problem and breaking it down into its most simple of elements. So for example, what are the greatest number of raw materials we have to work with to solve this problem? These 8 elements that make up the crust. I love that. And I also appreciate the fact that we're looking at that your research and that this project's direction really targeted the biggest hitters and who's generating the most amount of CO2 emissions from cement generation. So I really appreciate those perspectives. So one of the reasons that we have you on the podcast today is because you wrote this article called Alternative Materials That Could Shrink Concrete's Giant Carbon Footprint. And that's a big topic to tackle, and it's a lot of what you just touched on. In that article, you really discuss how this heated clay can reduce the carbon footprint of concrete. Can you tell our listeners more about that?
Yeah, I mean, first of all, I have to say that I didn't actually write the article. I mean, the guy who wrote it interviewed me, and yeah, so that's fine. But I don't want to take credit when
Fair
it's
enough.
not you.
You're the muscle and the expertise behind the content.
Yeah. I mean, basically, when you produce Portland cement, you first of all produce this product, which is called clinker. This is what comes out of these huge cement kilns. And in that process, you take, the raw material is mainly limestone, 80% limestone. Limestone is calcium carbonate. And what happens in this clinker production is that this limestone is broken down into calcium oxide and CO2. And the calcium oxide then goes on to react with other things to give you all the things in cement. But the CO2 is going off into the atmosphere. And this is actually 60% of the CO2 that comes from producing cement. Now, when you replace it with calcined clay, you've got 2 advantages. First of all, you have to use a much lower temperature. So instead of 1450 degrees Celsius you use for producing clinker, you only got to 800. But secondly, you don't have this decomposition of limestone. So that's the first thing. So for example, producing a ton of clinker gives you about 850 kilos of CO2, whereas producing a ton of calcined clay, you're between 200 and 250 kilos of CO2. So you can see it's much less. Now, but then there's another added element, which is the addition of limestone. Okay, I told you limestone emitted a lot of the CO2, but that's only when you heat it up to this high temperature. And if you add it afterwards, just by intergrinding, then it doesn't have hardly any association. So, it's almost negligible. So we have this dual effect, replacing a good part of the clinker by something with just much lower CO2 emissions in the calcined clay, and then with negligible CO2 emissions, which is the limestone. And overall, this means compared to a pure Portland cement, we can save about 40% CO2.
It's very cool. I'm curious, are you able to take into consideration the variations in different types of clay from around the world, or are they all consistent enough to where they work? Because I'm thinking here in North Texas, we actually have a form of music that's called red dirt music, and it's based on the red clays that are native to North Texas and Oklahoma. I know that clay looks different just about everywhere. How do you make up for those different variances in natural resources at the local geography?
Yeah. Well, the important thing is how much of what's called kaolin it contains. So probably some of your listeners may have heard of kaolin. It's, the component of, nice Chinese pottery and everything like that. And very pure kaolins are quite expensive. But in fact, most normal clays have some kaolin in, and we only need about 40% kaolin to get a good material we can use in this cement. And probably you can find good deposits in North Texas. Now, I mean, the red color is also an interesting aspect. The red color comes not from the clay minerals, which are these things like kaolin, but comes from iron oxide, which is also frequently present as well. And when we started this project, this was actually quite a big problem because people said, well, we don't want red cement. But in fact, you don't have to have red cement, even though you can start with quite a red clay, because the way you do this calcination, you can actually change the color to gray. I mean, Portland cement is gray because it contains iron. It's the same compound that's giving you this color. Iron is always giving you the color. I mean, that's why your blood is red, because it contains iron. And depending on how you do the chemical reactions, you can have it in different forms of oxidation, and that gives you either a red color or a black color. So people should be reassured they don't have to have red cement, but if they want red cement, then this is a good way to do it.
I just wanted to comment on the carbon footprint, how it is. You were saying like the LC3s are becoming more and more tested out in the field too. I think that's really cool. And I can even see it in North America, at least in California. You know, there's a lot of initiatives going on to reduce the carbon footprints, and the industry is very aware. We even have initiatives to reduce our carbon footprint. So things like these, I know a lot of engineers will be interested in, because we do realize the importance of it. And I think that's really cool that it is actually getting a lot of traction, in-field traction, practical applications. And yeah, to move on to my next question, what's the difference?
Can I just say something there? Because I
Sure.
think it's really, you know, again, going back to this question of suitable clays, you know, a lot of people start out and say, oh, we don't have suitable clays, we don't have kaolin. And California was one place where people said to us, we don't have materials. In fact, one of the very first uses of calcined clays, dating back nearly 100 years ago, was in California. And they do have very suitable clays in California. So, you know, we're really hoping that somebody will start producing in the near future, because we also see California as a place that's really concerned about these climate changes and willing to use these new materials. Sorry to interrupt you there.
No, absolutely. Yeah, it's a great point. It is. And it's great that, you know, it's becoming more public or industry standard. So that's great. Yeah, the next question was going to be, what's the difference between using CSA, I believe calcium sulfoaluminate cements, and Portland cement, and how does that affect our environment between using those two?
Yeah, well, you know, I talked to you about the composition of the earth and how we came down to these three oxides of calcium oxide, aluminium oxide, and silicon dioxide. In fact, in this system, there's really two basic areas. This is area of Portland cement, and this is area that then can produce these calcium sulfoaluminate cements, or also calcium aluminate cements. And these cements appear very interesting because you need less limestone to make them. And as I explained, it's the breakdown of limestone that's responsible for most of the CO2. So you can produce CSA cements with quite a bit less CO2 emissions. The problem is, to get these CSA cements, you need to have minerals that have very high aluminium content compared to silicon. And those are not found very widely. You basically have to go to something like bauxite. And bauxite, of course, is used to produce aluminium. It's a much rarer mineral. Something like 10 countries contain 90% of the world's reserves. It's expensive, but also it's not so abundant. So just to give you an idea, even if you stop producing any aluminium, you diverted all the bauxite we're currently extracting and used it to produce these CSA cements, you would still only be able to provide something like 10% of demand. And clearly that's, you know, that it just doesn't work in terms of resources. It doesn't work in terms of cost. And then you've got quite a few technical issues that it's not such a robust cement. The setting time can be quite variable. Other things, I won't go into all the details. But at the end of the day, even in terms of the CO2 emissions, you can get much higher reductions by going to this substitution strategy. So I told you that LC3, we can 40% compared to Portland cement. With CSA, you're only getting, for the materials most people are producing, you're only getting something like 20 to 30%. So that's quite a bit less. And then, you know, on top of that, you've got the higher cost, lack of resources and more difficult to use. So, I mean, to my mind, you know, LC3 is a much better strategy to go.
Very interesting. So you've covered two options right now. So LC3 and CSA. I believe there's a third alternative that you're pretty well known for, and that is geopolymers, that are another category of low CO2 emitting cements. And from what I understand, it's making quite a splash in the news currently. Can you tell us a little bit more about those?
Yeah, unfortunately, you know, this is something which I feel very sad about, because it's really diverting a lot of precious resources. It's diverting a lot of money, but a lot of young people into something which I really think is a dead end. Now, why do I think alkali activated materials are a dead end? These have been around quite a long time. They're not something new. They were first produced in the Ukraine, something like 60 or 70 years ago. And the ones that really work, all the ones that have been used in the field, because they work at room temperature, use either slag or high calcium fly ash. Now, I told you earlier that the amount of slag we had worldwide is very small compared to the amount of cement we need. It's about 8%. And we're already using 90% of that slag in cement and concrete. So in fact, if we took that slag out of the cement and concrete, holistically, we don't reduce any CO2. And in fact, we'll probably increase it, because we have to put these alkaline activators in these materials to make them work. So, you know, you've got a material where you've got a lack of resources. It comes out very much more expensive, because you have to put these very strong alkalis in. These cost a lot. They also have non-negligible CO2 emissions. They probably end up costing at least double what the cement we use today is, but you actually don't have enough material to make any significant impact, you know, on a worldwide basis. And then you have materials which are very complicated to use. They're very fickle. The setting time vary a lot between materials. And people have been trying to solve all these problems for decades. There's been billions and billions of research dollars gone into these kind of materials with no result in the field. And I think really it's frankly, it's so depressing to see that people are still chasing after this idea, which we can really see from the last 30, 40 years doesn't work, is never going to work, because we don't have the raw materials. And, you know, we should stop wasting money on this.
I'm so curious. So I appreciate your assessment and being so clear as to why these geopolymers maybe aren't as effective as other alternatives, and that we have clear data over years that proves that it really isn't making the dent that we want to see. Why are they getting so much press?
Well, you know, I don't know. You tell me. I think, you know, what you tell me. I think there's a problem of, you know, I think people want to find investment opportunities in cement, you know, and it's quite easy to get venture capitalists and, you know, show them this supposed wonder solution. They don't have the technical expertise to judge it. They invest, it gets very hyped up. And against this, you know, you take something like LC3, and, you know, we've done all of this with public money. Everything's in the public domain. And lots of people say to us, well, why don't you form a company? Well, the straight answer to that is there's between 2,000 and 3,000 cement plants in the world. If you set up your own individual cement plant, the impacts you have, it's peanuts. You're only going to have an impact in the real world if you get out there and you start introducing this in hundreds, if not thousands, of cement plants worldwide. And unfortunately, something you spend money on. So lots of people have come to us and said, oh, well, we really like you, we like to invest in you. Well, I mean, I keep saying, sorry, please give us a donation. That would be absolutely great. And you could have a real impact on global CO2. but I can't tell you you're going to get you're going to make money on it. And I just think that's really, really unfortunate. And, now we see more and more people trying to promote more and more crazy ideas. I mean, we've talked about CSA, we've talked about geopolymers. Another one, which is even worse, is people who say, oh, we can use bacteria or something like that to take CO2 out the atmosphere. And it's true, bacteria, algae, whatever, they can produce calcium carbonate. This is how corals work. That's absolutely fine. But they don't just need CO2 to produce calcium carbonate, they need calcium oxide, because that's just basic chemistry. And where are you going to get that calcium oxide from when nearly all the calcium on Earth is already in the form of calcium carbonate? Right? If you go to your chemical suppliers and you get calcium oxide, that calcium oxide came from calcining calcium carbonate, which gave off CO2. And then if you recombine that CO2 with algae or bacteria or whatever, you've achieved absolutely nothing. And there are dozens of companies promoting that technology. You go on their website, they're showing you all these wonderful things. We're fixing CO2 the way nature does in coral reefs. Please, invest your money into making sure corals don't get destroyed, because that's going to have a lot more impact on world CO2 than these so-called, biomaterials. I'm sorry to speak like this, but
no, not at all. I appreciate
it's really sad that so many of these companies are promoting these technologies.
Absolutely. So what you just described is effectively robbing Peter to pay Paul, right?
Yeah.
And when we're doing the CO2, we're not actually making any kind of a dent whatsoever. Well, the next venture capitalist I meet, I'm going to give them your contact information, because they do need the technical expertise to make the right decisions that are actually going to be impactful. And it's hard sometimes that where resources get put from a monetary standpoint are those that provide dividends, when we could be making a much bigger impact to everybody. So no, I love your candor, sincerely. This is awesome.
I'm sorry, and there's a lot of people who hate me for saying things like that, but nothing I've said cannot be factually verified. Everything is, basic science, basic chemistry.
Nope, I appreciate the candor. This is exactly why we want minds like yours on the podcast. So this is fantastic. No apologies required or allowed.
Yeah. No, yeah, completely agree. It's and I like the way you kind of set it up for the bigger picture, because as engineers, as scientists, it's not enough to just be right. You have to be effective to make an impact. And it's great that you see the bigger picture of that. And when you're talking about the plants and the corporations and whatnot, I wanted to get into I guess a sub question of that I had before I asked the next question is for LC3 and these other solutions. I'm wondering, are there economic incentives for owners, for example, for engineers, and we want to get this stuff like implemented, and we're talking to owners, contractors, architects. Is there like a off the top of the shelf, basically economic incentives, like this can save them money or anything like that?
Yeah, well, I mean, the short answer is yes, this can save them money. So I mean, that's the other great thing about LC3, that in fact the production costs in many situations are quite a bit lower than the Portland cement. So this is fantastic, because everybody talks about premiums for green products. This is all very well, but people just don't pay the extra money. So LC3 can be cheaper for the companies to produce. There can be some slight difficulties in adjusting to the use, but nothing really too serious, nothing we can't deal with the current admixtures we have available on the market. I think the main obstacle is just this kind of huge inertia in the industry. It's a very conservative industry. You have to realize that, a state-of-the-art cement plant may be producing 10,000 tons of clinker a day, 10,000 tons a day. You're not going to stop that production line and try out some new thing until you're really sure it's going to work. So, I mean, this is where our team really comes in. We have the technical team with us in Switzerland and in India, and they really can, do the testing for people. They can say, well, is this clay suitable? Give them the formulation. And this is what we've been doing over the last 7 years or so, and now it's really starting to show results. I mean, 7 years sounds a long time, but actually it's quite quick in this industry. So we're very pleased that it's starting to show results. As I say, we had 2 companies producing last year. We're going to see probably 4 this year, and I think it's going to go exponentially after that. And this would be a good exponential growth, unlike the exponential growth of COVID we've been suffering from the past year and a half.
Thank you for that. My last question is, in your opinion, how can we encourage more people to get involved in the material science of concrete?
Yeah, I wish I know. I wish I knew the answer to that. I mean, I think things are changing, because when I started in this field, I mean, when I used to say I worked on cement, people used to look at me and say, no, really, what do you really work on? Like I was making it up. And then they would say, well, yeah, but we must know everything about this. We've been using it for 100 years or so. And, and I think, you said you were a structural engineer. Structural engineers, they just have all their sort of codes and everything, and concrete is just concrete kind of thing. And what's really changing this is now this awareness that even though it's kind of a material with very low environmental impact, we're not going to help things by replacing concrete. We can make concrete a lot better. But this involves then understanding it as a material. So, I mean, we really want to make more bridges to structural engineers, the whole community, because also, I mean, LC3 is just the start of a chain. We start with the cement, but then we put the cement in concrete. And when we do that, we can also make savings. Then we put the concrete in a building. And when we do that, we can also make savings. And so we've got to be able to string all these parts of the chain together to achieve the CO2 reductions we need. And this really entails more dialogue between these different disciplines. Okay, so that I didn't get back to your question. Well, and how can we bring some more people in? Well, I think now, we see young people on the streets protesting about this. And I hope this is then going to mean that they can see that if they go into these engineering subjects, they really can do positive things. We calculate the potential of LC3 can be to save more than 400 million tons of CO2 a year. And people say to me, well, that doesn't sound that much. I say, well, it's 1% of world CO2. And they say, well, that's not that much. And I say, well, we only need 100 ideas like that, and we've solved the whole problem. 100 is not a very large figure. So come and let's work on it. And, I mean, it's really fantastic to be in universities at the minute, because, I'm on the promotions committee in EPFL. So I see all kinds of people, not of course in cement and concrete, but with all kinds of other brilliant ideas. The other day we had somebody who had a new system for cooling computers. The computers in data centers are also putting out huge amounts of CO2. So we need all these ideas, and I just really hope, and I feel young people are motivated, and hopefully then this brings about a change. But we also have to give them opportunities. So I hope funders and people like that are listening to this and see that we have to fund the right ideas.
Holy man, I gotta tell you, you got me pumped and energized, and I feel like I need to go pick up my spear and go be a warrior for these technologies right now. And this is the best platform we have to use. So I'm so thankful that you're here with us today. My final question to wrap this all up, you are so full of knowledge and wisdom, and my question to you is a little bit more personal. So for all of our listeners who are also equally motivated and jazzed right now, what is some career advice or industry insight that you would want to impart upon them?
Oh, I think the thing I always say to people is, don't give up. Like, everybody in their career has setbacks and times like they feel like giving it all up. And, I'm not going to go into all the details, but certainly I've had moments like that. And I think, hang in there, because you can do something. I think, look for things that have not been worked on in detail. I mean, that's what drew me into cement and concrete in the first place. I did material science, so I knew an awful lot about things that happened in metals. But then when I did a PhD, I thought, well, I don't want to work on metals because people have been working on that. They've found out a lot over the last 100 years more. I want to do something different. And then, a professor in London said to me, oh, yeah, we're working on this stuff called concrete. It's been around a long time, but in fact, how it works is still not well understood. And that really got me hooked. And, that's been what I've done ever since. So I think, don't necessarily follow the trend, think for yourself, but also, I mean, don't be afraid to, to really say, well, I'm just not going to accept what people have said in this field for a long time. I'm going to, think, is this supported by the evidence? I think these are all things, but at the end of the day, when I was doing science at university, scientists were always kind of regarded as nerdy and boring. And, it was the people who were doing literature and things like that who were regarded as having interesting lives. When I go back to my college reunion, I mean, I found that many of them went back to their places where they were born and then doing some fairly routine job. And I've had the chance to go all around the world, meet incredibly fantastic, motivated people everywhere, work every day with young people, which is always very motivating. And, I just think it's a really exciting career. Sorry.
No,
Awesome.
that's wonderful. I really quickly just want to kind of tie what you just said and wrap it up in a bow a little bit for our listeners. So you mentioned, if you're interested in doing something in this industry, go and do something that hasn't really been, all of the details haven't been fleshed out yet.
Yeah.
And I think that's a really great bit of wisdom to share, because most people who get into civil or structural engineering, they didn't decide to get into this because of the money or because of whatever that looks like. Yes, there's some job security there, or there should be, but the reason people get into this is because they're passionate about it. And you specifically said, don't be afraid to get to basically go into these areas that need more development and need more evolution. And I would like to think that most people who started in this when they first were, wide-eyed, excited university students, it's because they had a passion for it. And in order to use courage to develop your career, that means using heart. So not only using your brain to be able to design things, but use heart to put yourself in a position that you're going to grow. You're going to be out of your comfort zone. You're going to be out of the industry's comfort zone, but then you're actually making an impact on what the future of your industry looks like. And I think that's such a beautiful bit of advice to share with us. So thank you.
Well, thank you. I hope it's been useful for your listeners.
I think it's clear that it has. Yeah. I mean, Matt, I'm about to go back into design, which I would never do. And I'm going to go and start using LC3 in all of my projects. I'm ready.
Well, we'll be glad to discuss more with you further down the line, help you do that.
Perfect. Karen, thank you so much for joining us today. This was fantastic.
You're very welcome.
I hope you enjoyed the episode today. We'd love to hear your feedback, comments, and/or questions. To leave them, please visit structuralengineeringchannel.com. There you'll find a summary of the key points discussed in today's episode, which is episode number 50, as well as links to any of the resources, websites, or books mentioned during this episode. Don't forget to subscribe on Apple Podcasts or wherever you listen to your podcast. Until next time, we wish you the best in all of your structural engineering endeavors.